All right, we're back. This is page 3, continued of notes 2 of Calc C, and we are constructing our own polynomials. These things are called Taylor polynomials, and they fit a very specific pattern, and let's see if we can do this. So the 0th derivative is always the original function, and then on this one, we just got to remember the chain rule, like a lot. So we get this. And then it's like, once you've done this enough, you kind of know as soon as you're wrong because of you're getting the signs wrong and you're getting a lot wrong. I think I haven't gotten it wrong yet though. So that's encouraging, right? Sine of 2x, and then negative 64 cosine of 2x. All right, and then what we're going to do is we're going to sub in 0, which is called the center. So this is our center, and you'll see we're subbing it in there. So cosine of 0 is 1, so we'll get 1, 0, negative 4, 0, 16, 0, negative 64. Okay, and now we're going to take these, and we're going to try to fit them into the pattern. So it's going to be, so I'm going to write this a little bit more like I would normally write these. So p of x is going to be, so it's just the initial value, like the value of the function. That's 1. And then it's technically x minus 0 to the 0 over 0 factorial, but both of those are 1. So just leave it as 1. And then I do tend to write this. And you don't need to, because like 0 times anything is 0, but I find it much easier to continue the pattern if I've written that. But you know, you don't have to. So if you look here, you can see something really kind of interesting is happening where the all the odd powers are zeroing out, which if you think about it makes some sense because cosine's an even function. So if we're going to try to approximate it with a polynomial, it makes some sense that the polynomial should end up an even polynomial. And so if I simplify this, and then we're going to play around with the calculator a little bit just to get a better sense. So I don't believe in simplifying like the coefficient and the factorial. I don't know why I'm like having trouble getting that out, but I think that the pattern is a lot clearer if we don't do that. It's very obvious, well, sort of very obvious, that when you look at this, you can see like here that the second derivative must be that. And you can see, trying to use different colors here, that the fourth derivative should be 16. And I think you can see as well that you get that too, that the sixth derivative is negative 64. So you don't simplify them. It is unusual to simplify these beyond what I've simplified here. So let's see if we can use a calculator, figure these values out. Also, I mean, like if you look at this thing, so I don't mean to tell you your business, but if you look at this, another way to write this is 1 minus 2 squared x squared over 2 factorial plus 2 to the 4th x to the 4th over 4 factorial minus 2 to the 6th x to the 6th over 6 factorial, which is 1 minus the quantity 2x squared over 2 factorial plus the quantity 2x to the 4th over 4 factorial minus the quantity 2x to the 6th over 6 factorial, which is really interesting because if we think that cosine, right, cosine by itself, if we thought cosine of x was just 1 minus, and I mean, maybe we don't think this, but if we thought it was this, then it looks like to get from this to this, we kind of just did a substitution where maybe we made like u equal 2x, and like every x that we saw for cosine, we replaced with 2x, right? So it probably would have been better to call this cosine of u. Here we go, ready? I'm gonna try to delete and fix that. So here, if we made this u squared, u to the 4th, u to the 6th, it looks like maybe we can just do compositions on these. Like if we have a simple thing, maybe we can get a more complicated one just by doing a composition. And we'll find out more about that as we go along. let's compare the values and see how it went. So like, is it always guaranteed to be a really good thing? Like, not really, because usually you need like an infinite number of terms for these to be exactly the same. And like, obviously you don't have that. But usually a couple of terms is enough for it to kind of like get close. And so here, and that's what we have. We have, you know, 4 terms, 4 non-zero terms. So non-zero terms is going to be a big deal. Those are just terms that aren't zero, right? Like, so every other term here is 0. We saw that because every other derivative evaluated to 0, but we only have 4 non-zero terms. And so usually it's the non-zero terms that you end up like kind of counting this, and that'll be the cosine of 2x. So I'm gonna, I guess I need to fill in the table. So, all right, f of x such that x equals the sequence -3 plus t comma t 0 to 6. So it's the function that's generating the sequence, the variable in that function, where you want it to start, where you want it to end. So first it plugs in 0 for t, then 1, 2, 3, 4, 5, and ultimately it'll plug in 6 for t, which gives us x equals +3. So this will fill in the table. So let me do that. 0.9. Oh, I'm using the wrong color. Not that anyone can see, but like that's why, that's the delay here. Also, I'd like put a random. All right, I'm good to go. Don't worry. 0. No, I'm not good to go because I'm trying to write with the eraser. Man, if you could see the mess I'm making. Oh, whoa. Okay. So the first one's positive, then the next one's negative. That's interesting. 654, -0.416, exactly 1, because that's cosine. -0.416. So this is an even polynomial, so it should be just symmetric here, like exactly the same. And it is if you look. 960. Okay, and then we got to also plug into p of x. So why am I copying done? I'm going to just change this f into a p. P, and then, okay, here we go. Look at all these 2's. What is happening here? All right, so it's terrible at -3, and we'll see that in a second when we look at the graph. Like it's off by like 30 almost. So 27.8, -2.022, -0.422, exactly 1. It's exactly the same at the center, which it always will be. -0.422, and then we kind of know it's going to be like -2 and then -27.8, but -2.022 and -27.8. So it's horrible at the endpoints. Let's take a look at the graph and see why it's terrible at the endpoints. I mean, you can kind of think it through, because like a 6-degree polynomial is going to like peel away really fast at some point. So let's see if on the graph we can see that. So f of x, and then p of x. And so you can see, like, look at in this interval though. It's so good. Like right like here. It's amazing. You can't even tell that there's 2 graphs. That's how close they are on that interval. And then as you get farther away, it'll get worse because you should have an infinite number of terms in your polynomial, which would create a series, an infinite series. But we have a finite number, so eventually it's going to stop being right? If we like add one more term, so what would the next one be? The next one would be plus 2 to the 8th, fraction, 2 to the 8th, x to the 8th. I'm just following the pattern that we seem to have found. This, you can see that it's good, but now when it's wrong, it's going to be so wrong and so far above what we were actually expecting to get. So if you don't have an infinite number of terms, it's not going to be exactly the same. But neither is a tangent line, right? So always go back to what you knew about those sorts of things. Tangent lines are good for a little interval, and then they start getting progressively worse. Taylor polynomial is going to be good for an interval, a bigger interval than a tangent line, but eventually it's going to get worse. So there's a lot going on with these. And the key things, I think at this point, you can make your own table. You really want to know the pattern, although at some point we'll write it down definitively, like in a box or something, but you really want to know the pattern so that you can take advantage of it. And then the approximations, right? You're approximating values, so you're not going to be right. You're just going to be less wrong the more terms you use. All right, so I'm going to end this video here and come back in the next one and do more. So I will see you there.